Hi, this is Professor Fernandez, and this is video 2 in lesson 12. We're still talking about related rates here, and we're going to do a slightly more involved example than we did in video 12.1. I do want to encourage you to check that video out if you want a review of related rates in general. And also, in that video, I talk about box 4.1 down here. I'm just going to zoom in really quickly to show you what that is. This is my suggestion for how you might set up a related rates problem. And there's kind of 4 steps here, and I'll use that throughout this video, but encourage you to go to video 12.1 if you want to see more of the details about why those particular 4 steps are what I suggest. Okay, so let's read through this example. It says you are inflating a balloon that remains spherical as you inflate it. Okay, so one of the first things in that box 4.1 is to draw a diagram. So there's a balloon here, and it remains spherical as you inflate it. So I'm trying very hard to draw spheres here. And this is, as time goes on, you inflating the balloon. So the balloon's volume V and the radius R are related by this equation. This is the volume of a sphere with radius R. Great. So we kind of have some sense of what's going on here. And the hint that this is going to be a related rates problem comes in the next paragraph. Suppose you inflate the balloon such that R changes at the constant rate of 0.1 inch per second. So what I mentioned in that box 4.1 is that look at the units to determine which rate you're given, inch per second. So over here, I'm going to put this information as, I'm going to use these units to tell me which one of the variables I'm being given information about. So 0.1 inch per second, it's telling me that R changes. So this is the rate of change of R with respect to time, equals 0.1 inch per second. Okay, and another thing I mentioned in that box 4.1 over here is that you want to think about the context of the problem. So we are inflating the balloon. So the radius, like I drew over here, one of the reasons you want to draw a diagram, the radius is getting bigger. So because the radius is getting bigger, the rate of change should be positive. In this case, dr dt should be positive. So we don't want to put in a negative 0.1 inch per second. That would be a decreasing radius. That would be a deflating balloon. Okay, so we have this information, the RDT. Let's keep reading, see what else we have. Here's the question that makes it related rates. How fast is the volume of the balloon changing when its radius is 6 inches? Okay, so the question here is how fast is the volume changing? So volume here is V. So we're asking about dV dt when the radius is 6 inches. When the radius, which is what we called R here, when R equals 6 inches. Okay. So you can see what I've tried to do here, and I'll go over it very quickly. This is what's in box 4.1. First, I tried to draw a diagram. And then next, I tried to take the information I was given and using the units as a guide, write down the rates that I was given and select variables, right, R and T. Then I went off and I found the question, right? Here's the question right there. And it was, how fast is something changing? That is a prototypical related rates question. And I tried to mathematize that also. The volume, V, with respect to time, T, and then when the radius is 6 inches, that's over here. Okay, so I can't stress enough, which is why I'm taking so much time doing this, how important it is to set up the problem carefully and correctly. Because once you translate all of this, mostly English up here into math, right? If you do it correctly, then the rest of the steps are an application of the chain rule, like we did in the previous video. So let's do that right now. So if we want to find dV dt, we need a formula for V. In this problem, we're given that V is the volume of a sphere. We're given V of R, right? But remember, R is changing with respect to time. So this is the formula that is going to relate the rates, dV dt and dr dt. How do we do that? We talked in the previous video, 12.1, about 2 ways to do it. I'm going to use the Leibniz version of the chain rule here. That's a little faster. So I'm going to say that dV dt is dV dr. Why am I choosing r? Because v is a function of r, times dr dt. So that's the Leibniz version of the chain rule. Great. dV dr is something that I can find from the formula I'm given, right? R here is being cubed and it's being multiplied by 4/3 pi. So V is basically a multiple of a power function, right? R cubed. So I'm going to use the power rule to differentiate it. So the derivative of R cubed is 3R squared. and then 4/3 pi goes along for the ride as a multiple. So 4 pi over 3 times 3r squared. That is dv dr. And then I multiply it by dr dt. Pretty soon I will use what I know over here about dr dt, but I'm not going to do that yet because I'm going to do a little simplification here. So these 3's cancel, and I'm left with 4 pi r squared dr dt. This is the equation that relates the two rates in this problem. The one that I know information for, and the one that I'm trying to find information about. Okay, so now is when I'm going to go off and down here where there's more white space, first of all, write down my equation relating my rates, 4 pi r squared dr dt. And then I'll just substitute in everything I know. So dr dt is 0.1 second, inches per second. That goes there. And then the 4 pi, that's a number. And then r, this is where I go up here. I want to find dv dt when r equals 6. So I'm going to put that in there. So I get 4 pi times 36 times 0.1, and that ends up being about 45.2 numerically. So now let me just pause there to talk about the units. So another nice thing about Leibniz notation is that you can easily tell the units based off of what's in the numerator and what's in the denominator. In the numerator, we have a volume. We have measured the radius of the sphere in inches. The volume would be inches cubed, so that goes over here, inches cubed. In the denominator, we have t. We've been using that as time, right? dr dt was inches per second, so that goes in the denominator over here. And at this point, we have solved the related rates problem, right? We found dv dt when r equals 6. We also included our units, so that's the end of the related rates problem. Last thing I'll say here is, again, reiterate how important it is to set up the problem correctly. Because again, after we set up the problem correctly, this was just an application of the chain rule, and then substituting in the information that we had, and then some simplification, and out popped the answer. So really, related rates boils down to setting up the problem correctly. So again, I encourage you to check out the previous video, which talks more about this box 4.1, or just rewind through this one and see in detail how we went through these 3 and 4 steps down here to find our related rate.